Hello everyone, and welcome back. Today we're going to continue our exploration of differential equations and focus on a very important theorem associated to the existence and uniqueness of solutions for first-order differential equations, whether they be linear, nonlinear, exact, non-exact, doesn't really matter. First order, this theorem is going to help us guarantee the existence of a unique solution to an initial value problem, and also discuss an iteration method that you can use to solve or sort of solve differential equations regardless of how complicated that they may be, in case you don't have any other methods that might be able to solve them, assuming that you're not resorting to numerical methods, at least not yet. So, the first theorem that I want to discuss, at least the only theorem today, is known as the Picard, or some people also call it the Picard-Lindelöf Theorem, and it says the following. So suppose that R is a closed rectangle with x0, y0 belonging to that closed rectangle. So keep in mind x0 is our initial condition x value and y0 is going to be our initial condition y0. So as long as your initial condition is in this closed rectangle and this function f, where f is associated to that, differential equation y prime is equal to f xy, as long as this function f is nice, then we should have a unique solution that passes through x0, y0 within this rectangle. That's sort of what we're going for. So f has to satisfy two criteria. It has to be a continuous function in terms of the independent variable, and it has to be Lipschitz continuous in terms of the dependent variable y. And if you don't know what Lipschitz continuous is, that's okay. I'll just give you a quick rundown of what it means to be Lipschitz continuous. So that means for all points x1, x2, belonging to R, and of course x1 and x2 need to belong to that domain of f, then there exists a real number k, and this real number has to be the same for all x1, x2, and that k must be a positive number such that the following condition holds. The absolute value of no big absolute value, but the absolute value of x2 minus f of x1 all over x2 minus x1, this must be bounded above by that number k, right? And keep in mind that that's always bigger than or equal to 0. Right. So in some sense, if you look at this expression fx2 minus fx1 over x2 minus x1, that's almost like the derivative, right? So it in some sense imposes a bound on how fast that function f is allowed to grow, right? Now k could be 5 billion, 5 trillion, 5 trillion factorial, as long as that k exists for all x1, x2 in R as inputs of that particular function f, then we say that that function is Lipschitz continuous in y. Right, so if this is your particular expression, this means that we're f is Lipschitz continuous, Schitz continuous, in the variable fx, and you can extend it to the fxy case as well. Right, so if you want to sort of extend this to our case, that means there exists some k such that 0 is less than or equal to the absolute value of f. Some variable, let's call it zeta x2 minus f zeta x1 all over x2 minus x1. So this is what we're going for in terms of that expression. And that could be also zeta 2 and zeta 1. And that has to be true for all x1, x2. Right? So that's what we're going for Lipschitz continuous, but if you're not interested in the theoretical details, that is particularly okay, at least for now. Right? So let's assume that f is continuous in x, Lipschitz continuous in y. Then, if that is true, there exists some positive number epsilon such that the differential equation that we're primarily concerned with, where y is a function of x, and that's set to be equal to x y of x with the initial condition that yx0 is equal to y0 has a solution, and it has a unique solution. It has a unique solution, yx, supported on x0 minus epsilon x0 plus epsilon, i.e. that's contained hopefully within that closed rectangle R that we mentioned before. Right? So that's what the Picard-Lindelöf theorem says, and the criteria that it says that must be true in order for that unique solution to exist for an initial value problem. So generally speaking, as long as your f is a nice function, then you're going to have a unique solution for an IVP. Right? So if we sort of think about this, I'm not going to prove the exact result because it requires some things that I don't want to mention here. But our differential equation y prime is equal to fx yx. If that y was not inside that function f, for example, if we just had, like x squared minus sine of x, that would be a separable equation. We can multiply both sides by dx and integrate, and then we'd be done, right? So in some sense, if we want to get rid of this integral, this derivative expression, in some sense what we want to do is we just want to integrate that function. But we can't integrate the function on the right-hand side, at least not directly, because it also has y in it. So if we have, for example, y prime is equal to fxy, this of course would be an ordinary differential equation, but if we have y is equal to the integral of fxy dx, that's not a differential equation, that's an integral equation. Because now our unknown function is underneath an integral rather than underneath a derivative operator, right? But actually, these are more natural to solve, at least numerically. Because when we're actually solving for this function y, and keep in mind this is still an implicit solution to the differential equation at least. It might be a different type of equation, but it's an implicit solution to the original equation. All we're doing when we're solving differential equations are just evaluating integrals in some sense. All right? But actually, you can do this with no issue at all. So if we have y prime of x is equal to f of x, y of x, with initial condition that y of x0 must be equal to y0, then when we take the integral with respect to x of both sides, what we're going to have is y of x is equal to some constant c, but one can show that that constant is equal to y of 0, plus the integral from x0 to x, because x0 is our initial condition, therefore when our arbitrary solution has a variable x and it's greater than or equal to x0, of that function f of t, y of t dt. And we have to switch variables there because we're integrating with bounds that are x dependent. Right? So we have this particular expression. So one can show that this is indeed a solution to the original differential equation. And I highly, highly, highly recommend that you verify that this is a solution to y prime is equal to fxy. Right? So this is indeed a particular solution to that differential equation, right? And if it's a particular solution by the Picard-Lindelöf theorem, we then have that this is the unique solution. Now, that expression doesn't look quite useful, but it actually gives us some enlightenment of a method that we can actually use to solve differential equations, which is known as the Picard's iteration method, which I'll now get into. So now that we have some criteria underneath us, at least informally, of the existence and uniqueness of solutions for initial value problems, now what we want to do is sort of explore, okay, well, if it exists, how can we find it? Would be nice. And if we can't find exactly what it is, maybe we can get close to that function, step by step maybe. And this is not a numerical method because we're not using any approximations, but what we're doing is we're going to iterate a bunch of solutions that are eventually going to get close to the solution. And this method sort of comes up in the formal proof of the Picard-Lindelöf theorem, or at least one of the proofs of it. So this is not just some magic made-up thing. Like, you can actually prove with this method that the solution actually exists and is unique, assuming that those criteria for f and y actually were held. So what we're going to begin by doing, so we're going to have some differential equation, y prime is equal to fxy with initial condition, yx0 is equal to y0, and we're going to begin our iteration method by defining phi0 to be equal to our initial condition value of y. Then, so that's our initial condition, and if you've ever worked with any iterative methods, such as the Newton-Raphson iteration or the bisection method, we usually have a initial condition or an initial guess per se of what that solution actually looks like or is close to, hopefully. Right? So that's our initial guess or an initial condition, and every other condition is going to be based on the previous guess. So it should get better and better and better as we work through this recursion loop. So our next iteration and everyone thereafter is going to be based on that solution, which indeed is the unique solution, from the Picard-Lindelöf expression theorem, right? So we have that is going to be our y0 in disguise, plus the integral of our function f. Now keep in mind we do not know what y is equal to, therefore this is our old value of y, and this is our new value of y, and we're just going to nest them inside of each other, and one can show if the solution does exist, then this sequence will converge to the value of y, right? So provided a unique solution exists, then this sequence is going to converge to our particular solution yp as the number of iterations get arbitrarily large, right? One can prove that as well. Right? So with that behind us, let us actually work through an example of finding the solution via this iteration method. So the differential equation I want to work with is actually a very easy one, and you should be able to solve this on your own without this method, but you at least can check that this method actually works, right? But you would typically use this on equations that are not easy to solve, right? For example, non-exact equations where you can't find that integrating factor. So we're going to have y prime minus y minus xy is equal to x with the initial condition that y0 is equal to 3, right? So our x0 is 0, our y0 is equal to 3, so that's our initial condition location. And once we rearrange this, we're going to have y prime is equal to x plus xy, which means that our f of xy is equal to x plus xy, and more importantly, f of t, y of t, is equal to t plus t times y of t, right? T times y of t, right? Because we're going to be using that expression there, right? So we do notice that this is a first order linear inhomogeneous differential equation, so you can use integrating factors to solve this to get the exact solution, but let's assume that we don't know how, because generally speaking for non-easily solvable differential equations, you don't know how, right? So let's assume that you do not. So the initial iteration, phi0, is always going to be equal to our y0 value, and in this case, our y0 is equal to 3. And from here, we're going to define arbitrarily our k plus 1 iteration, which is going to be equal to y0 plus the integral from x0, which is 0 in our case, to x of f of t y of phi k, which is going to be equal to t plus t phi k. And this is going to be true for k greater than or equal to 0. So this is what we're going to apply over and over again, and what you're going to have in the end is an infinite series that hopefully you can recognize. But if you can't recognize it, that's okay. If you can't recognize it, at least you have an approximation for the solution. So what is phi 1 going to be equal to? So it's going to be equal to 3 plus the integral from 0 to x of t plus t phi 0 dt. And keep in mind that phi 0 is just equal to 3. So we have the integral from 0 to x of t plus t times 3 dt. Right? So once we have that, we actually has a very nice solution because that right there is just 4t. So we have 3 plus the integral from 0 to x of 4t dt, which is equal to 3 plus 2t squared evaluated as t goes to x as t goes to 0. Since we're working with a polynomial here, the bottom limit's always going to go to 0, and you can, in some sense, shortcut this and always say, okay, well, that's just equal to 2x squared, right? So our initial guess was equal to just 3, is rarely ever a good approximation to the exact solution. But starting with the first iteration, at least we see, okay, well, that looks like a parabola. So our solutions also might be parabolas or even functions, maybe like cosine. It could look like, for example, hyperbolic cosine or something like that. It's an even function. At least it appears that way after the first iteration. But, just an order 2 approximation probably isn't a good approximation regardless. So let's get a couple other terms and sort of see what's happening. So, phi 2. So phi of 2, again, is going to be equal to phi of 0, always in the lead, plus the integral from 0 to x of t plus t times the last iteration, which is going to be equal to phi 1 dt. So we're going to have 3 plus the integral from 0 to x of t plus t times phi 1, which is 3 plus 2t squared dt. So once we have this term, then we can sort of sit back and analyze. The goal for the Picard iteration method, if your goal is to get a nice pretty solution that's not a power series, is try to pick up on any patterns as quickly as possible. And if it's not a power series or pattern that you've ever seen, you probably won't be able to observe it. So don't feel bad in that case. It's okay. There's infinitely many patterns. We probably only have seen maybe 50 of them, maybe. Really depends on what level you are. So what we have here is once we distribute this t in, we're going to have that 4t term just like we had from before. So we're going to have 3 plus the integral from 0 to x of 4t. And then over here we're going to have 2t cubed. Integrate with respect to t, of course. And then from here we're going to have that phi 2 is equal to 3 plus 2x squared plus 1/2 x to the power of 4. And we still see that, okay, well, at least our pattern's building. There's our phi 0 term. This is our phi 1 term. This is our phi 2 term. So we're getting close to, I guess, in some sense, the polynomial, right? Hopefully, it's converging. Hopefully, at least, right? If a unique solution does exist, it will converge. That much is guaranteed from the Picard-Lindelöf theorem. Right. So again, we still have an even function, so we would expect that the next term is probably going to be like x to the 6th, followed by x to the 8th, x to the 10th, and so on. So the next thing that we have to do is, okay, do we see any pattern with these coefficients? 2 iterations probably isn't enough, so let's just do a couple more, just so we have some idea of how to build a more accurate approximation in case we don't get a pattern. So phi 3 is going to be equal to 3 plus the integral from 0 to x of t plus t times the previous iteration phi 2, which was 3 plus 2t squared plus 1/2 t to the power of 4 dt. Once we have that, once we distribute that t inwards, that's always going to increase that degree by 1, and integrating will always increase it another degree. So 3 will go to 3 something x squared, t squared will go to something t4, t4 will go to something t6, and in terms of those reference terms, I'm looking on the interior value. And also notice that this portion was the same as the previous iteration. That's going to create that stacking term. So what we have here is 3 plus 2x squared plus 1/2 x to the power of 4. Over here we're going to have 1 over 12 x to the power of 6, right? And if we do, for example, phi to the power of 4, you're going to have 3 plus 2x squared plus 1 over 2x4 plus 1 over 12 x to the power of 6 plus the next term is going to be 1 over 12 times 8 x to the power of 8. And do you see the pattern yet? So 5 is going to be 3 plus 2x squared plus 1 over 2 x to the 4 plus 1 over 12 x to the 6 plus 1 over 12 times 8 times x to the 8 plus 1 over 12 times 8 times 10 times x to the power of 10. Right? So in some sense, what are we exactly looking at here? Right? Now, I believe, did I make any silly mistakes? I don't think so. No, we're safe. Do you see any patterns in terms of these coefficients in the bottom? So on the bottom, we're going to have 1 times 2. On the bottom, we're going to have 1 times 2 times 6. Over here, we're going to have 1 times 2 times 6 times 8. Over here, we're going to have 1 times 2 times 6 times 8 times 10, right? So it's almost like we're multiplying all of the even numbers, right? But if we look very, very carefully, we actually have a lot more than that, because notice that there's a 2 hiding inside of this 6. There's a 2 hiding inside of that 8. And there's a 2 hiding inside of that 10. So we can also write 1 times 2 as 2 to the 1 times 1. We can represent 1 times 2 times 6 as 2 to the power of 2 times 3. We can represent 1, 2, 6, 8 as 2 to the power of 3 times 12. And we can continue this expression onwards, and maybe you can guess what the next term will be, right? But notice that these are sort of offset by some values as well. So maybe we can sort of start shifting things and sort of guessing what that pattern might be. Now, if you're not interested in getting the exact solution, this might be where you decide to stop or go up to as many terms as you're asked to go up to, right? But if you are interested in possibly generating a power series representation, you have to be very, very clever and open-minded on how to generate that representation. And again, the pattern doesn't always exist or is not easily noticeable, right? So from here, it's really optional, but sometimes gives you some enlightenment on the beauty of recognitions of patterns. So if we look at this F5, this 5, 5 in disguise, what we have here, again, so I'm going to use the previous observations. I'm going to write this as 3 plus 2x squared plus x to the 2 times 2, because that's the same as 2 times 1, all over 2 to the power of 2 minus 2 times 2 factorial. So I'm sort of decomposing that 1 over 2 times x to the power of 4. Then I'm going to move on to that x to the 6. I'm going to have x to the 2 times 3 all over 2 to the 3 minus 2 times 3 factorial. And then I'm going to have x to the 2 times 4 all over 2 to the 4 minus 2 times 4 factorial. And then we're going to have x to the 2 times 5 all over 2 to the 5 minus 2 power times 5 factorial on bottom. And that would be 5, 5. And from here, if you see the pattern, then it's very, very simple. Because we see that 5, 5 is just going to be equal to, and you're like, okay, well, what about this particular term right there? So that should be equal to x to the 2 times 1 all over 2 to the 1 minus 2 times 1 factorial. But what's 2 to the 1 minus 2 on the bottom? Well, that's just 1 over 2 to the minus 1, which is equal to 2 on top, which it is, right? So what about that first term? Well, that would be equal to x to the 2 times 0 all over 2 to the 0 minus 2 times 0 factorial, which would be equal to 1 over 2 to the minus 2, which is equal to 4. But it's not 4, it's 3, right? So we can always represent 3 as 4 minus 1 in order to sort of force the pattern into that particular expression, right? Which is what we're going to do. So from these observations all combined, we have the 5, 5 is going to be equal to the sum from k is equal to 0 to 5 of x to the 2 to the power of k all over 2 to the k minus 2 times k factorial, and don't forget the minus 1 at the very end. Now, if you don't like this 2 to the k minus 2 power, keep in mind you can write that as 2 to the k times 2 to the minus 2, and keep in mind that's on the bottom, which is the same as 4 divided by 2 to the k, and we can factor that 4 out of the summation if necessary. Right? So from this, we can then generalize this using mathematical induction and say that the nth iteration of this is just going to be equal to 4 times the sum from k is equal to 0 to n of x to the 2k all over 2 to the power of k times k factorial minus 1. Right? So if the unique solution exists, and indeed it does, then the true solution, the particular solution, is going to be equal to the limit as n goes to infinity of the nth iteration of this series, provided that our function f(xy), which is equal to x plus xy, is continuous in x and is Lipschitz continuous in y, which it is. Right? So life is good there. So this is just going to be equal to 4 plus the sum from k is equal to 0 to infinity of x to the 2k all over 2 to the k times k factorial minus 1. Right? And you're like, well, that doesn't look like a familiar function. Well, it almost looks like one because we can represent this as 4 times the sum from k is equal to 0 to infinity of x squared divided by 2 all to the power of k all over k factorial. So it's something to the k over k factorial, which you should recognize as an exponential function. So we have 4e to the x squared over 2 minus 1 as your exact solution, and you should be able to use the method of integration factors for first order linear and homogeneous equations to verify that as well. But notice that we were able to get it through very clever algebraic manipulations using the Picard's iteration method. But again, if you're not interested in going through these in some sense non-obvious algebraic manipulations to get a closed form, which likely doesn't always exist, it's sometimes sufficient if you're just looking at an approximation of just getting as many terms of that series as you can and saying that, okay, this appears to be a 10th order approximation to whatever function it is, and at least from the first 5 iterations of this method, it appears to be an even function, which e to the x squared divided by 2 indeed is. All right, so that's the Picard-Lindelöf theorem and its consequence in terms of the Picard's iteration method in order to approximating or even luckily converging to the exact solution of that initial value problem. Hope you enjoyed this video, and I'll see you in the next one. Take care.